Hello and welcome to today's lesson. I'm Bodo Kanrindo of Italian students of Mathematics KNUST. Today we're talking about the Couette flow. Recall that in our previous video, we said we had types of flow in terms of fluid dynamics. We had the pulsate, the Couette, and we can have the general flow when we combine these two types. In our previous video, we talked about the pulsate flow, and in this video, we're talking about the Couette flow. So the Couette flow is represented by this diagram here, where we have this plate 1, plate 2. So the fluid is placed between two parallel viscous plates, and there's our fluid here. So the movement of the fluid, or the fluid, is driven by the upper plate, the motion of the upper plate. So at the starting point, our velocity is 0, but at our y-end, the velocity is equal to some u. And in the case of the pulsate where the fluid was driven by the pressure gradient, here the pressure gradient is 0 because the fluid motion is driven by the movement of the plates, upper plates. So the Couette flow is driven by the motion of the boundary upper plate moves, right? So that's the most important thing. So now we are coming to derive the velocity profile, shear stress, and the rest for the Couette flow. So from the equation of motion, minus the PdS plus mu del squared u del y squared equals 0, which we've already discussed in the pulsate flow. So when you make the PdS a subject, we have this, right? So the negative sign goes away. And trying to make del squared u del y squared the subject, we get this. So this equation is very important here. Notice this. But note this, that for Couette flow, boundary conditions are such that the top plate moves. That is, when y equals 0, u equals 0, but when y equals yn, u equals some big U. You've already explained it in the diagram I showed you before we started. Also, note that there is no pressure gradient. That is, the PdX is equal to 0. So, now let's try to find for the velocity profile. So in the equation above, we have this, right? But we are seeing for the Couette flow, there is no pressure gradient. It's equal to 0. When you put the 0 here, you're going to get this equation here. So that means we'll get del squared u del y squared equals 0. Then when we do the first integration with respect to y, you're going to get del u del y equals a certain arbitrary constant. Let's call it c1. When we do our second integration, you're going to get u of y equals c1 times y, then plus c2. And this here happens to be the general solution for the velocity profile. But we have initial conditions. We are supposed to use that to find for the particular solution. So the first initial condition is that at the starting point y equals 0, the velocity is 0. So putting that into this equation, you're going to get 0 will be equal to c1 times 0 plus c2, meaning c2 is equal to 0. Then the second initial condition is that when y equals yn, our velocity equals to capital big U velocity, because the motion is driven by the motion of the upper plates. So here we are going to get u be equal to c1 y end, right? Because y is equal to y end, and our c2 is 0, so we don't have anything here. So making c1 the subject, we get c1 will be equal to u over y end. So we know that the general solution was given us this here, but we've gotten c2 and we've gotten c1. So making in substitution, we are going to get our u be equal to uy over y end. I hope you get it. Where this u is the velocity profile, and this u is the velocity at y equals y end. Right, so this happens to be the velocity profile for the Couette flow. Then we have the shear stress. So with the shear stress, it's given by tau equals mu del u del y. So we have our u here. So when you find del u del y, we're going to get u over y end. and putting that into the expression gives us what we have here. So this happens to be the shear stress for the Couette flow. Then where the maximum velocity occurs is y equals yn on 2. Alright. And then with our maximum velocity, so to find for our maximum velocity, we substitute y equals yn into the main velocity profile equation u of y. That will give us u max equals yn over 2yn. So this cancels this. Then finally we have u over 2. Then the discharge is giving us ko equals the integral of u dy. So u is the velocity profile, which is uy over yn dy, and our limit of integration is from 0 to yn. So doing this integration is going to, we can pull u over yn out, then we have this. When we integrate, we have this. So putting in the limit of integration is going to give us this, and one of this will cancel one of this. Then finally we are going to get uyn over 2, and this will be the discharge. Then we can find the average velocity, which is also known as the u mean. So that is given by the discharge over the flow rate. So know that the flow rate is always given by yn, and the discharge is what we just computed here. That means that our u mean will be equal to uyn over 2 divided by the yn, and this is the same as uyn over 2yn. So this cancels this, and we have u over 2. I hope you get it. Right, so some useful relation here is that you realize that u mean is equal to u max. Can you see that? So know that u mean is given us and u max is also given us. So we see u mean is equal to u max. But if you could recall from that of the policy, that one it was u max was equal to 1.5 u mean. But with this one, u max is equal to u mean. So thank you very much.